example problem. Okay, so it says an isolated conductor sphere whose radius R is blah 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 has a charge Q. So how much potential energy is stored in the electric field of this charged conductor? What is the energy density at the surface of the sphere? Okay, so when we consider a sphere conductor, and yeah, it only mentioned the radius, which means that it doesn't have the outer plate. So we will use C equals 4 pi epsilon naught R using this expression. And actually, we need to find the potential energy, which means U equals Q squared over 2C, which is actually this one. So yeah, so we can just substitute Q squared over this expression to here. So we have 8 pi epsilon naught R. Okay, so substituting the values there, we have Q is 1.25 times 10 to the minus 9 power, and then quantity square over 2 times 1 over 4 pi epsilon naught is actually 8.99 times 10 to the 9th power. Or actually, we can just simply write it as Q squared over 2R and then 1 over 4 pi epsilon naught, something like that. And this is actually K. So we have K here. So 2 times R is 0.0685. Yeah. And then yeah. So the answer will be 1.03 times 10 to minus 7 joule. Okay, so it is quite simple. And this is part A. And for part B, what is the energy density at the surface of the sphere? So we will make use of this U equals 1/2 epsilon naught E squared, which will be 1/2 times 8.85 times 10 to minus 12, and then times E squared. Let me see. E squared will be K, which is 1 over 4 pi epsilon naught times Q over R squared, and then the whole term squared. So it will be K squared Q squared over R squared. Okay, so we have a K squared Q squared over R. R to the fourth here. So we have a 8.89 times 10 to the 9th quantity square times 1.25 times 10 to the minus 9 quantity square all over 0.0685 to the 4th power. And it will be 25.4 times 10 to the minus 6 joule per meter cube, or you could probably write it as 25.4 microjoule per meter cube. So it will be easy. It will be easy. Okay. So next, we here talk about some hardcore physics. So it is about the capacitor with dielectric inside. So previously, when we talk about the capacitor, it is about two parallel plates, and between the capacitor, it will be probably air or vacuum, something like that. And for air or vacuum, the conductivity will be similar, will be very, very similar. So not much difference about that. But here we will try to insert something called the dielectric between the parallel plate, and it will influence the characteristic of the capacitor. And the dielectric, for the dielectric, in Chinese, this is called 电介质. Okay, so if the space between the plate of a capacitor is completely filled by a dielectric material, the capacitor C in vacuum, just mentioned, vacuum or air will have a similar conductivity. So it's multiplied by the material of the dielectric constant. So it introduce a variable called the dielectric constant. It's a Greek letter kappa, Greek letter, not K. It is a Greek letter kappa. So which is a number always greater than 1, always greater than 1. So this is an important property, because you will learn in chapter 33, when you learn the EM wave, you know that the speed of light, 光速 will be 1 over mu naught epsilon naught. In this is a speed of light in vacuum or speed of light in air. And yeah, so you can see epsilon naught is what you have learned here, which is 8.85 times 10 to minus 12. And mu naught, you learn it in chapter 28, which is the permeability, which is 4 pi times 10 to minus 7. So when you plug in the values there, you will calculate the speed of light will be something like 2.998 times 10 to the 8th power meter per second. And also for dielectric, epsilon could be like kappa times epsilon naught. And as much as kappa is always larger than 1, which means that the epsilon for other materials such as dielectric will be always larger than epsilon naught, which makes the speed of light in other material will be always less than the speed of light in vacuum. And yeah, this is what we have observed. And and also the special relativity also have this assumption. Actually, you will learn this in this dimension. Okay, so just come back here. So we have the dielectric constant kappa and the permeability. Sorry, not permittivity. Permittivity. Permeability should be the mu naught. Permittivity of the dielectric will be kappa epsilon naught rather than epsilon naught only. So in a region completely filled by dielectric material, the dielectric constant kappa or electrostatic equation containing the permittivity constant epsilon naught are to be modified by replacing epsilon naught with kappa epsilon naught, which is some textbook it will write it as epsilon only. Okay, so if the potential difference between the plate of a capacitor is maintained, as by the presence of a battery, the effect of a dielectric is to increase the charge on the plate. So yeah, so you can see here. So you can see here for this state, if a battery with a voltage difference V, then there will be less charge here. And if we just insert the dielectric between the capacitor, the charge increase, Q increase. Why it will be like that? Because if you still remember, the capacitance of a parallel plate capacitor will be C equals epsilon naught A over D. So for this case, it will be C equals kappa epsilon naught A over D, like this. And as I mentioned, kappa will be would always be larger than 1, which means that C, let's say this one is C prime. C prime is larger than C. And as much as you know, V for both cases are the same. So you know CQ equals CV and Q prime equals C prime V. So as C prime is larger than C, so Q prime will be larger than Q, like this. Okay. So another case is that if we just put some charge on the capacitor, and we try to measure the voltage difference, which means that for this case, Q and Q remains the same. And we try to insert the dielectric between the capacitor, and we find that the voltage or the voltage difference or the potential difference between the parallel plate will decrease. So here we have a Q to be constant. So similarly, we can see that C prime is larger than C. So we will try to have V equals Q over C, because Q equals dV, so V equals Q over C. And V prime equals Q over C prime, because Q is the same. So, and we have a C prime is larger than C, which means that V will larger than V prime, like this. So this is the other case. So far it will be easy. Okay, so this is some hardcore part of the dielectric, hardcore physics part of the dielectric. So just try to understand it in any sense. Actually, not really important if you don't really understand it. Actually, I don't know what it is, but yeah, I try to explain it. Yeah, so here, dielectric is something like there are many electric dipole in the material. So an electric field is applied, producing partial alignment of the dipole. Thermal agent. Any questions? Okay, so apply producing a partial alignment to the dipole. Thermal agitation prevents complete alignment. So so here molecules with a permanent electric dipole moment show their random orientation of the absence of an internal electric field. So as you have learned in, I think, chapter 22 or 23, I don't really remember. So if you just put some molecule, just such as H2O, H2O is a is an example of the dipole. So the dipole will look like that. And if initially it is not oriented with the same direction as the external E field, then it will keep swinging back and forth. It will keep swinging back and forth. So it can just keep the molecule to be partially alignment. So they tend to rotating to the same direction as the external E field, but yeah, it cannot just stop there, because as long as a dipole just move to this status, then there will be some torque to just some angular frequency to rotate it to the other side. So it cannot be so perfectly aligned. And for the polar dielectric, if you don't apply any external E field to it, then all the dipole will be just like randomly aligned, which means that all the dipole moment will somehow cancel each other, which means that it will not generate E field. But if you still remember, if for a single dipole, of course it will generate E field like this way. So yeah, so the interesting stuff is here. So as much as we have non-polar electric, which means we do not apply any external E field to it, then they are just randomly aligned, so it will not generate E field by itself. So if you just apply an external E field to it, so this is parallel plate, so it generate. So this is the capacitor. So if you charge by some constant voltage, there will be some charge, and it is a parallel plate with charge, so it will generate constant E field pointing to the right side. In this case, the dielectric will, the dipole inside the dielectric will start to align perfectly with the same direction as the external E field. So it will be somehow like the positive side will interact with the external E field. So there will be something like E field pointing to the right side. So there will be a force dragging it to the right. And for the negative side, as long as the E field still point to the right side, so the Coulomb's force will point to the left side. So you try to drag all the dipole align with the external E field. So in that case, all the dipole are aligned. So in that case, this dipole, all the dipole will generate E field. Like, so you can feel like as much as you have all the positive charge on the right side and negative charge slightly to the left of it, which feel like the center of mass of all the negative charge is slightly to the left side, and the positive charge is slightly to the right side. So it will generate E field pointing to the left side, which means that so this is E0. E0 is, E0 is the external E field. E0 is the external E field. Then E prime is the E field generated by the dipole, which will cancel parts of the external E field. which makes the E field, the total E field, so this is the total E field inside the dielectric, will be smaller than the external E field. This dielectric will cancel part of it because some of the energy is absorbed by the dielectric. So it makes the E field inside the dielectric to be smaller, because if you still remember, energy is proportional to the square of the E field. So it absorbs part of the energy, which makes the E field inside the dielectric to be smaller. Okay, so this is the hardcore part. So an energy is that, so if you are in the classroom taking the class, and if it is, the lecture is on, then suppose all of you will just look at the right board, most of you at least, I think. But if it is not on the class, then probably you will just maybe chatting with other classmates, or maybe you just go outside to buy some drink or take some water. Then you may be somehow like randomly orientated, not actually all of you will face the right board like that. So it's an analogy to the dielectric. So here, inserting dielectric into a capacitor causes induced charge to appear on the base of the dielectric and weaken the electric field between the plate. So just I mentioned, if there is no dielectric between, then there is external E field, which is generated by the parallel plate, which is known as the capacitor. So if we just put some dielectric between the capacitor, then it will generate an E field, which is opposite. This is generated by the dielectric, which will cancel part of it. It cannot be larger than the external E field because it is absorbing this energy. So it will only make the total E field inside the dielectric to be smaller. Okay, so when a dielectric is present, the Gauss law may be generalized to this one. Actually, you may concern why we don't write it as a kappa epsilon naught integration of E dot dA equals Q enclosed. So in the textbook, it says the kappa might be non-uniform, might be non-uniform. So you just put it inside so that you can consider it inside the integration. Just for that reason. But for at least in this course, I will not ask you to integrating some strange material. When Q is the free charge, any induced surface charge is accounted by inducing the dielectric constant kappa inside the integral. So the textbook also mentioned this variable called the dielectric displacement D. Although it's seldomly used in other chapters, it only appears in this chapter. So just maybe just keep it in mind. It is not so useful in this course, and so it just write epsilon kappa E as D only. So this is pretty much it. Okay, so let's take a look at this sample problem. Okay, so here, a parallel plate capacitor whose capacitance C is charged by a battery to potential difference V between its plate. The charging battery is now disconnected and porcelain slab kappa equals 6.5 is slipped between the plate. what is the potential energy of the capacitor before the slab is inserted. Okay, so this is pretty easy to find. The potential energy is nothing but U initial. So before the slab is inserted. So 1/2 CV square. So easy. 1/2 times 13.5 times 10 to minus 12. And then times 12.5 quantity square. Okay, so this is 1.055 times 10 to the minus 9 farad. Joule. Or maybe you can write it as 1.055 nanojoule. Okay, so easy. So what is the potential energy of the cap slab device after the slab is inserted? Potential energy. So before we insert the slab, it is C. And the battery is now disconnected. So we have a Q. We have Q and V. So as much as we have C prime with the slab slitted in with the slab. In that case, Q doesn't change because the charging battery is now disconnected. So the charge has no way to go. And in that case, V prime will change. So Q doesn't change. Q has charge has no way to go. So C prime and V prime will change. So in that case, C prime will be kappa C, which is 6.5 C. Because what I mentioned is C equals kappa epsilon naught AD. C prime. C equals epsilon naught A over D. Like that. So C prime equals 6.5 D. So UF will be Q squared because Q doesn't change. So Q squared over 2C. Actually, you can also calculate it by 1/2 C prime V prime square. But actually, you need to also find V prime. So to make things easy, we can just make use of a Q squared over 2C. So it is 13.5 times 10 to minus 12 quantity square over 2 times. This should be C prime. So this is a 6.5 times 6.5 times C prime. Yes. Not this way. Not this way. D. Sorry. This is D. So Q equals CV. CV. So it's times 12.5. Q equals CV. Also quantity square like this. Should be like that. Okay. So C prime should be 6.5 times 13.5 times 10 to minus 12. Something like this. Okay. So this is 1.62 times 10 to minus 10 joule. Or you can write it as 162 picojoule. Okay, so still very easy. So the next, yeah. So yeah. So actually, the delta V W will be Ui minus UF. Yeah, potential. Yeah, actually W is Ui minus UF, which is 1.055 times 10 to minus 9 minus 1.62 times 10 to minus 10, which is 8.93 times 10 to minus 10 joule. Although it is not asked by this question, but actually it means that the potential energy decrease. The potential energy decrease, which means that if you just place the slab near the capacitor, near the capacitor, the parallel plate, then it will be just absorbing it between the plate, so that it could absorb some of the energy to make the energy become smaller. Okay. So next, we have another sample problem. So it says a parallel plate capacitor of a plate area A and plate separation D. So we have separation D. And then a potential difference V0 is applied between the plate. The battery is then disconnected, similar to the previous one. And a dielectric slab of thickness B. B is smaller than D. So there will be some gap between the slab and the capacitor. So yeah, it's placed between the plates. Assume AD, V0, B, and kappa. What is the capacitor C0 before the dielectric slab is inserted? Okay, so yeah, so this is easy. C0 equals epsilon naught A over D. So this is 8.85 times 10 to minus 12 times A is 115 centimeter square. Actually, we need to convert it back to meter square. And you know, 1 meter is 10 square centimeter. So 1 meter square is 10 to the 4th power centimeter square, which means that we need to multiply it by 10 to the minus 4 to make it a meter square. Yeah. And then D is this one, 0.0124. Okay, so this is 8.21 times 10 to minus 12 farad, or 8.21 picofarad. Yeah. So next, yeah, we know this value. So what recharge appears on the plate? So it is still very easy. Q0 equals Z0 V0. Yeah. So this is 8.21 times 10 to minus 12 times V0 is this one, 85.5. So this is 7.02 times 10 to minus 10 Coulomb. Okay, so far so good. Okay, so next, what is the electric field E0 in the gap between the plate and the dielectric slab? E0. So now we need to use the Gauss Law. Yeah, use the Gauss Law. So let me write down the Gauss Law first. Epsilon naught. Yeah, because what is E0 between the plate? So because we only consider the E0, which means that E0, which is outside which is outside the dielectric. So we only consider the case without the kappa. Integration of E dot dA equals Q. Okay, so we consider Gaussian surface 1 because we would like to know E0 here. So E0 will cross this surface. There will be no E field crossing the upper surface because this is conductor, so there's no E field inside the conductor, and so as this tube. And so we consider the Gauss law for the Gaussian surface 1. So as much as it is uniform, so it is nothing but epsilon naught E0 times A equals Q. Yeah. So E0 is nothing but Q over epsilon naught A. So let us plug in the values, 702 times 10 to minus 12, and then over 8.85 times 10 to minus 12 times A is still the same, 115 times 10 to the minus 4th power. So this is like 6,900 volt per meter. So which is quite a strong E field. So next, it asks, what is the E field in the Dielectric Lab? So E0, we just find it. So there will be another E1 inside the dielectric. Of course, E1 will have a magnitude smaller than the E0 and with the same direction as I mentioned before. So now we apply the Gauss law for the Gaussian surface 2. So here we have let's see, we have let's see, we have epsilon naught integration of kappa E1 dot dA equals minus Q. This is pretty interesting. Although it says there will be some charge inside here, but actually when we really count the charge enclosed, we don't really count that Q bar because it is somehow like they are dipole. So even though there are some effective charge inside this area, but totally it will be quite small. So or in another point of view, we already consider it with the copper, so we don't count this Q bar repeatedly. Yeah. So let's see. We consider the Gauss law for the Gaussian surface 2. So for this surface, there will be no electric flux. So we don't count this two phase. For this one, this is a conductor, so no E field inside the conductor either. So no contribution here. So the only part which will contribute this integration is the upper surface, which is like E1. E1 is pointing inside. E1 is pointing inside, so it's a negative value. So we have kappa E1A, kappa E1A, and then epsilon naught equals negative Q. So, or maybe you can directly write in and E1 minus sign here. So it is like kappa minus E1 like this. So it makes E1 to be a positive value, which is the magnitude of the E field. So E1 will be Q over kappa epsilon naught A. So which is 702 times 10 to minus 12 over 6.5 times 8.85 times 10 to minus 12 times 115 times 10 to the minus 4th power, like this. So E1 will be 2640 volt per meter. Oh, sorry, this is not 6.5. In this question, the kappa changed to 2.61. So here it should be 2.61. That yeah, so 2.61 is that. So which is like so actually this part is E0, which is like E0 over kappa, which is like this one, 6900 over 2.61, which is this value. Okay. So next. What is the potential difference? What is the potential difference between the plates after the slab has been introduced? So as we mentioned earlier, if we just put in the Dielectric Lab, the capacitance will change. The capacitance will change. But yeah, the capacitance will change. And now it is disconnect. The battery is disconnect so that the charge wouldn't change, which means the potential difference between the plate will change. But in this case, there are some gap between the dielectric and the parallel plate. So it is like there are different capacitance in series, something like that. But let us consider what it really look like. So we try to define a path from the negative plate to the positive plate. We integrating this part from the negative side to the positive side. And if you still remember, the potential difference V between the parallel plate will be the integration from negative to positive E ds. So ds pointing upward. E is pointing E is pointing downward. Okay, so let's see. We don't necessarily need to consider the direction anyway, because originally, which is like V equals negative E dot ds, something like that. Then we need to consider the direction of the dot product, and here we already tackle with that direction already, so we don't need to really consider the direction of the vector. Yeah. So here, which is like for this part, E1 pointing downward, and maybe let me just erase some of the make it more clear. So we have E1 pointing downward. We have E0 pointing downward. Of course, this is uniform, but I try to separate them a bit to make it more clear. Otherwise, you just like a line or pointing from the top to the bottom. Okay, so for this part, it is E1 and it is uniform inside the dielectric. So it is E1 times B. E1 times B. And for this part, and this part, we don't necessarily know what is the length. We don't necessarily know what is the length of this part and this part. But yeah, we only consider the sum. So the total height of this part and this part will be just d minus b, because this is b, this is d. So this part plus this part will be d minus b. And then the E field inside this part and this part are also uniform, and which is E0. So E0 here. So what we have calculated is that E1 is 2640 times B is 0.0078. So careful. This is centimeter, so 0.0078 plus 6900, and then this one is 1.24. 0.0124 minus 0.0078. Yeah. So V is 52.3 volt. 52.3 volt. So of course it is smaller than V0 as expected. V0 is this one. V0 is this one. 85.5. After inserting the slab into the parallel plate, then the potential difference dropped to 52.3 volt. Okay, so next part is what is the capacitance with the slab in place between the plate of the capacitor. So it of course becomes smaller, but actually this is not just simply kappa C zero, something like that. It is not that case because the height of the dielectric slab is smaller than the distance between the parallel plate. So actually, we need to calculate by C equals Q over V. Q over V. So Q, or Q0 over V. Q is 0 over V. So Q0 is 702 picofarad, which is times 10 to minus 12, all over this one, 52.3. 52.3. So which is like 1.34 times 10 to minus 11 farad, or you can write it as 13.4 picofarad. Yeah. And actually, if you still remember, C0 is this one. C0 is 8.21 picofarad. Like that. Okay, so we finish off this chapter and let's have a 10 minutes break.